And we're going to call this functions. So make sure you're doing these with me. Let's start by writing the definition. A function is a rule. On Desmos, what wording did we use? It said that assigns, I like to use the word matches. It's a rule that matches exactly one output. And we're going to make a little change here too. With outputs, since they're in the table, and we've already used tables before, sometimes we call those y's. It's in the right side of the table. You're keeping track of what's coming out, so we can call it just the y. A function is a rule that matches exactly one output, or the y value, to each input. And inputs are sometimes called the x value. So to be able to find and explain a function today, what we're doing is we're looking to see if the inputs and outputs match. Okay, let me know if you have any questions as we're going. Let's draw a table to show kind of how we determine that. So I'm just going to draw an XY table, but remember X is input, Y is output. Here it is. Not too big. We're just going to keep it short. We're just going to use 3 values. It's the minimum amount you could try. Usually you need to try more than 3, but we'll keep it to 3 for our notes. And with the inputs, the nice thing about functions is you get to choose whatever you want. There's no pattern. You can make a pattern if you want, but it doesn't have to be. Like, I'm just going to say, let's try 35. Let's try 723. And let's try -4. We're going to plug them into some sort of machine, some sort of rule, and we're going to see what comes out. The screen looks blurry. You know what? Let me try. I changed the setting. Let me change the setting back real quick. If I go like this, if I go, let's see if that's any better. Does that look any better to you?
It's a bit darker.
Maybe darker. Does that look okay like that? Or is that weird now?
It's good.
Okay. So this is how you set up a function. One way to do is make a table and then just show us what inputs you're going to use. And then there's a rule, and we don't know what the rule is. We're not so worried about those today. I mean, maybe you'll figure it out as we go, but that's not our purpose. Our purpose is just figure out if it's a function or not. So let's say on this thing, we put in a 35 and we get out 25. Let's say we put in, let's see, 723 and we get out 713. We put in a -4. Let's say we get out -14. So based on that, we look at the outputs and inputs and we see if they match. If it is, this is a function. Oh, can you tell what the rule? Yep, there's the rule. Can you tell what the rule is? Mm-hmm. Good. Yep. Yep. So sometimes these can get really complicated. So I'm going to show you a strategy to figure out, to determine if you have a function. We use tables. That's method 1 is use tables. And we do this thing called mapping. We're going to use tables to map. We're going to map inputs and outputs. And it's not that complicated. It just sounds complicated, but it's not. This is how you map it. We go back to the table and I take my input 35 and I'm going to draw a line to show me what comes out when I put in 35. When we put in a 35, we get a 25. This is what's called mapping. 723 gives us 713. -4 gives us -14. When it's all nice and neat like that, it shows that each input matches to exactly one output. So this would be a function. And you actually figured out what the rule was. But let me show you one where the mapping doesn't look all nice and neat like that. We'll do another table over here. Again, X's and Y's. We're going to try the number 15. We'll try the number 16. And we'll go back and try the number 15 again, just because you can. You can choose whatever you want for your inputs. When you put in a 15, you get out a 0. When you put in the 16, you got out a 32. When you put in the 15, you got out a 4. So this right here already is showing like something weird's happening here. So there was some rule that was changing all these numbers. But when I put in a 15, I got out a 0. So I can map it like that, draw my arrow. But when I put in the 15 again, I got out a 4. So I'm going to draw another arrow that goes down to the 4. That means that this is not predictable. When I put in 15, why did it change? I don't know. Functions don't do that. The 15 should always make a 0. But because it made a 4, because this now has like 2 arrows going to 2 different outputs, that means that this input matches 2 outputs. But that's not how functions work. It has to match exactly 1. So this would be not a function. And you could show it with a mapping, just like that. And once it fails, you don't have to map all of them. I can just stop there. That's enough to show me, nope, it's not a function. Questions, comments, concerns, wonderings? If you wanted to, you could map all of it. You could map the 16 and the 32. And then when you get to this bottom one, you would map it to the 4 and also up to the 0. But again, you don't need to do all that. As soon as it failed once, it's done. For functions to work, functions have to work every time. If there's ever a time that you get 2 outputs, well, then it doesn't work. It's not a function. Okay? So that's method 1. That's one way you could figure out what you're looking at. We're going to talk about method 2 now. We could also use graphs. That's what method 2 is, to use graphs. We've dealt with these tables before, and we know that in these tables, these are just ordered pairs, 35 and 25, 723 and 713. And if we wanted to, we could take all those ordered pairs and we could graph them, and we could see what does this function look like. Or in this case, we would graph them and say, well, what does this not function look like? And the question is, well, what if we didn't have the ordered pairs? Could we just use a graph? And let me show you what that would look like. We're going to draw a coordinate plane. It doesn't matter how big, just, I don't know, kind of like that. And then we'll draw that's our y-axis. Here's our x. Again, the size of the coordinate plane doesn't matter. I do want to kind of keep it even though, kind of keep it balanced, something like that. And our y-axis is up and down, but these are what we call the output. And the x is what we call the input. So let's say with this one, we got some results, and when it graphed, let's say it looks something like this. Let's say It started up here in the top left, and I don't know, let's just say it went like down, and it like went right below the x-axis, kind of like that. And then let's say it bounced back up, kind of made a V shape. And you know what? Let's make it bounce back down again. Let's like that. So that's kind of a weird kind of like zigzag line. And I'll go over it in the highlighter here so you can see it separate from the coordinate plane. So here's the graph of inputs and outputs for some sort of machine. Something's going on with these numbers. The question would be, is this a function? So how could we figure out if this is a function or not? What do you think you'd want to do? What would you be wondering? Or what do you notice? What do you think? Thoughts, ideas, wonderings? There's an idea, maybe no, it's not a function. It's not a straight line, so maybe not. It's going up and down, so maybe not. Okay, so mathematicians wondered about this for a long time. They were thinking, all right, well, you know, I don't have like all the numbers in a table. I just have it in a graph. How could we figure out if that was a function? I mean, we could make a table if we wanted to, but that would be extra work. Is there a way we can just look at this and figure it out? And so here's what they figured out. Here's what they did. First, you have to think about the definition. It says that we're matching the inputs and the outputs. So what they thought was, okay, well, let's look at all of our inputs. All the inputs are along this line, right? There's like an infinite number of them. They're just all on this line somewhere. So what we want to know is, does everything on that line match to only one output? Because that's what the definition is. So you can kind of think of it as in pieces. Like, what if I told you that we were, I don't know, like right over here? I don't know what that point is. It looks like it's at 1, 2, 3, 4, -5 maybe. So if our input was -5, could you tell us the output? Sure, you could. You would go over here and you would say that number is your output. That input matches to that. Or let's say we were like over here. Let's go over here at the very end. Let's say I told you, hey, this was my input. Could you tell me the output? Well, to figure it out, you would go down and you'd say, well, it's that, whatever that y is. And so it'd be like that number over there. You'd say, well, yeah, I can tell you the output. It's that. So as long as that always works, as long as you can always tell us the output, then it's a function. So what they do is this thing called the vertical line test. They take these lines and you run it along the whole graph. And so the best way to do it, I like to just use my pencil, is I just start from left to right and I run it along the X, because what I'm doing is I'm checking every input and I'm saying, do I know the output right now? Yep, I know my output. It's always where this line is touching my pencil. So there's my output, it goes down and it comes back up and it goes back down again. So it's kind of weird, but does it always touch my pencil just once? Yeah, so this is a function. It's a weird function, but it's a function because it passes the vertical line test. Everywhere along there, your pencil only touches the line once. Questions, comments, concerns, wonderings?
Wait, if you make a line right where you kind of made, where it's X is, wait, sorry, if you count this way. where X is 6 and Y is 4, won't that touch twice? Oh wait, X is -4, sorry.
Kind of right here.
No, actually, sorry, my thing is very small. Keep going left. Yeah, right around there. If you go up, won't at one point like if you make a line couple up, yeah, won't it touch the other?
The only thing I'm noticing is like the arrow at the end here. The arrow just means that the line keeps going forever that direction.
Okay.
So it looks like it always touched it just once. But
Oh,
yeah,
I thought it touches like it counts as the whole graph, so it only does one quadrant.
you don't even think about the quadrants or anything. All you think about is just running your pencil along the line.
Okay.
Because it's going to touch like an infinite number of times. There's always going to be some places touching the line. The question is just, is there ever a time that it touches it twice?
Oh, okay, got it.
And so for it to happen, for it to touch twice, it'd have to be like this line over here, instead of going forever that direction, like if it like turned and like went back this way, then when you run your pencil along it, it actually touch it twice. Like we'll look at some of those examples in a minute. But yeah, so thank you for wondering about that. Over here, it looks like if we try like these inputs, we're still going to get one output. It's just going to be different every time. Okay, let's go back to the Desmos. Yeah, okay, we'll talk more about the pencil thing here in a second. Let's go back to the Desmos and let's kind of try to use our notes now.